Good morning. Good morning, everyone. Am I audible? Okay, good. All right, yep, let's get started. We have been talking about partial order planning. So we'll continue from there, and then in today's lecture, we'll also see graph planning. So partial order planning, what we have seen is you given a problem, right? You start with two dummy steps. The steps are the start state, and so this is what you do, right? So in partial order planning, you start with the start and finish. There is no effect of finish. There is no precondition of start, but then there is a set of effect for this start, and there is a set of precondition for finish. And you what you do is essentially every time choose one of the sub goal, right? So there are multiple goals. You choose one of the sub goal and try to satisfy it using by choosing some other operation, right? So you choose some other operation which pre post condition or effect. Yeah, so which effect satisfies the precondition of sorry, so which effect satisfies this sub goal. So essentially, if you look into partial order planning, it has just three main steps, right? So try to write. So what are these three main steps? One is you have this start and finish, right? So that's you define these dummy steps, and then what you do is you select your sub goal, right? Selecting one of the sub goal, and then choose operator to fulfill the sub goal. This is what you do, and then after doing this, you resolve any thread, right? So that is very important that it should not lead to some inconsistencies. So you resolve threads. So let's write this partial order planning in a formal way, and the algorithm, right? So just to understand things in more formal way. So partial order planning algorithm is nothing but a function. This is POP, partial order planning. It takes certain things, right? So what are the things it takes? One is the init state, or the goal is start state, initial state, not the start state. Goal state, right? The what you want to achieve, and of course the set of operators, right? And what does it returns? It returns plan. It returns plan. Right. So this is the signature of the partial order plan algorithm, which takes initial state, goal state, and set of operators, and returns plan. So what you do is initial the first step of your is plan. The first state is you make minimal plan. Right? What do you mean by minimal plan? Make and this should definitely take the init and goal. Minimal plan is nothing but you have this you add these two dummy steps, start and finish, and this is the minimal thing. You can say that you also know the ordering of them, right? So you know that as start step should be executed before end step, yeah, or before finish step, and you define the preconditions and effects of start and end state based on start and finish state based on this init and go, right? So that's the minimal plan, very minimal, and then from there you refine, right? So refine means you do some kind of a looping, right? So the next is loop. uh, loop. So inside loop, first thing is, if that minimal plan itself is the right solution, then you are done, right? So if plan what you get is a solution, right? So a solution means it should be complete and consistent, then return plan. Obviously, many cases this will not going to happen, right? But this is, if you are lucky, just initial and goal. Nothing needs to be done. And this when will this happen? This will happen only when your init start and goal states are same. Otherwise, this will not going to happen in the first place, right? So inside loop, you have to do something. What do you do? Second, the third step. Third step is you select some sub goal, right? So if you remember this figure, we said that you select these sub goals, right? So you need to select these sub goals. Again, details we will write of these functions separately, but here I'm just writing it in a like signature form. So as need C, what step is needed, right? So what step is needed from the set of steps, right? So that is one thing. Second is you need to have the precondition C, right? So precondition which you want to satisfy, and that being said, that will be given by select subgoal. So how do you select subgoal? We will write this function separately, but for now it is just select subgoal of given a plan. Right? So given the plan, you are going to select subgoal. Fourth is you choose some kind of a operator, right? So you choose some operator so that this can be, this C can be, or S needs, right? So S need and C can be satisfied. So your fourth step is, again we will write the details of this. Choose operator, right? And this you are going to choose given plans, given plan, given set of operations or operators, and of course the S need and C. Okay, and the final state is the fifth state of this fifth step of this algorithm is resolve threads, right? So that's very also very important, that you do not have any threads, right? So if you remember last class, there was a thread like if you go to bookstore and without buying book, if you go to tea store, that's not a good plan, right? So that will not, that will lead to some inconsistencies. So resolve thread will also take plan and done, right? So these are the just 4-5 steps of this POP algorithm. Now let's look into detail of these functions like what does select sub goal does, what does choose operator, and what is resolve thread. So these three functions now we are going to see in detail. Okay, let's look into function select sub goal. Function is select sub goal, and it takes plans as input and it returns as need and see. So how do you write it? So it's simple. It's very simple. You can pick a plan step as need from plan step as need step of plan. Right? One of the step you choose, one of the state you choose with a precondition C that has not been achieved. So it's like you are choosing one of the state, and in that step you are seeing that or if you are checking that are the precondition achieved. So you choose one of the precondition which is not achieved, right? So you choose with precondition. So please try to connect these things with the examples we took, otherwise they will not make much sense. That has not been achieved, that has not been achieved, right? Like you are taking one of the sub goal here as a input, right? And then you return as need. Let's see. These two things you return. Okay, so next we are going to write choose operator. We have another function called choose operator. So let's write it here. We have a function called choose operator, and we said that it takes plan, it takes uh, operators, yes, need, takes. So it does something. Maybe better not call function because function means it does something. So some procedure which does something, right? So on this thing. So what is it going to do? You are going to choose some operator which satisfies this precondition, right? So you write one, choose a step, right? A step. Let's call it as add from operators or steps of plan, right? That has an effect. So you are choosing that operator which has an effect. C that has an effect. That has C has an effect. That has C as an effect. Recall that what you do is uh, let's say you have to satisfy a precondition of a state like have t, then what you do is you choose by t, right? So by t has an effect, by t has this effect c, right? So by t has an effect have t, therefore you choose by t. But if there is no such step, what will happen if there is no such step, return fail, right? So this is you are going to return fail. If that's not the case, then what you are going to do is you are going to add causal link, right? So you add causal links link. What type of causal link you will add? Can anyone tell me, so that I understand that where do you add? You add it to the links of plan. Yeah, can anyone tell me what type of causal link will come here? You are choosing a step as add, and you have the S need, which you are going to satisfy the precondition of that C. So what kind of, from where to where the causal link will be there? S need to S add? No, so it should be S add to S need, right? So because S need is what you are going to satisfy, right? So the direction will be S add to S need, right? S need to S add. No, S add to S need, and the C is what you are going to achieve from that causal link. So this will be added in the links, and then you also have to add some ordering. What type of ordering you will add? So you need to add the ordering constraint. Add ordering constraint. So the ordering constraint will be your S add should happen before S need, right? So this will be added to ordering plan. This will be added to ordering of plant. Now, if SAD is newly added step from the operators, then now if SAD, right? So SAD we have said that SAD is a operator. If it is a new operator, which we have not been used so far, or it's a new step which we have not even used so far, so then we need to add it, right? So we need to add SAD to steps of plant. Is need to be added. So add this step to this if it is a newly planned, and we also need to add ordering. That what type of ordering we need to add? We need to say that start should happen before S add, and S add should happen before finish. Very trivial, but this is also need to be added. To when we add this, you need to add it to ordering. Right? So this you are just saying that you have new state, so you are maintaining this ordering constraint that this new state is also will also going to be following the rule that start is first, then this is head, and then finish. Okay. Okay. So now the last step that is resolve thread. This is again a procedure. Procedure is resolve thread. And it takes plan as input. Right. So what is a thread? For each S thread that returns Si to Sj in links plan. So let's say there is a thread, right? So we have seen what thread is, like in the last class. For example, if a thread is actually like a step which produces negative effect, right, to the other step, right? So, like for example, if the precondition of going to, let's say, going to the store is at home, if, if that is a precondition, if then there's some other step which produces as an effect not at home, will thread the net, right? So we need to be careful about such threads. So what is a thread is like for each S thread, let's call it S thread, that threatens threatens a link, a link, uh, okay, a link, let's call it SI to SJ, SI to SJ in links of do. What are you going to do is, so okay, so here a question. So what will be the effect of S thread? Anyone? What will be the effect of S thread by looking into this? Can you tell what will be the effect of S thread? Not C, correct. That's correct. So S thread will have effect and not C. Now what you do is you do either promotion, promotion or demotion. What are these things? We will see. Promotion means what you do is you promote S thread. Sorry, yeah, you promote S thread as compared to uh, SI, right? Sorry, uh, yes. So before doing SI, you do S thread, right? So that's kind of a promotion of S thread. So S thread is given a preference. S thread is promoted as compared to SI, and this ordering is added to. We were added to where orderings of plant. Demotion, on the other way, is you demote threat, right? So there's threat operation or step, threatening step that that threats SI to SJ. So you demote it. That means you first finish SI to SJ, right? So you first finish SJ. SJ is first finished, and then you do S threat. All right, and this will be added to ordering. This is called demotion. Why demotion? Because S thread is demoted as compared to SJ, right? So you prefer, so if you try to write this promotions and demotion figure, this is what is happening. I will tell. Let's call it SI. This is SJ, and then this is C, right? And then there is a S thread. S thread. Okay, let me write it. S thread. This has an effect C dash or not C, right? So sorry, not C. So what in promotion, what you are doing? You first execute S thread, right? And then you execute this. So this is promotion. The black arrow is showing promotion, while let's use the red arrow to show demotion. All right. So that's the red arrow is demotion. Black one is promotion. Right. Okay. So this you do, and then you check. Then after doing these things, you check if the plan is consistent. or if not, let's say, if plan is not consistent, then fail. Right? If there is some violation in the ordering, like transitivity violation and such thing, then you fail. Otherwise, it will be done and it will get something. Okay. All right. So with this, we end the discussion on partial order planning. Yeah, and as you can see, the partial planning is like it's very interesting algorithm as compared to state space. It's more like how we people choose actions, right? So, or how do you act in the real world? Because if you have many sub goals, many like if you have a goal to achieve, you try to achieve sub goals, but this is kind of extremely slow in real life. Right? So around 95, 97, there is in AAAI 97, I guess. There were two guys who talked about a different planning strategy altogether that is called graph planning, and that these plannings are more popular these days. Uh, so graph plan, let me see where it was. Which we are going to discuss now. So graph plan was in 95, a AAA paper was there. Uh, that is by Evrim Blum and Mary Frost. So this was it takes input as a planning problem expressed in scripts and produces, if one is possible, a sequence of operations for reaching a goal state. Okay, so now I will discuss graph planning for graph plans. But before that, maybe we can take a couple of minute break. And if you have any question or any concern, we can discuss. Graph plan. We'll take a couple of minute break and start. It's 8:30. Okay, so come back. So we're going to talk about graph plan. So graph plan. is very different from the like state space plan. So graph, we have also seen graph in terms of in case of state space, right? So let's first take an example to understand what this is as compared to state space planning, right? So we have seen state space planning in the a couple of lectures back versus graph plan or planning graph. Sometimes people call it planning. There is a big difference. Let's understand from an example what is the difference. So in state space plan, each node is a state and the edges are actions, right? So you do some action and then you get into some state, and there is a each of these nodes are a state, and you search in that space of state. In planning graph, your nodes are prepositions, a set of prepositions, literals, and also so there are two types of node in planning graph. One is the nodes which are actions, which represent actions, and one is the set of literals. So this is a kind of a layered graph, and where the first layer is of literals, second layer is of action, third layer is of literals, and fourth layer is of actions, and so on. And all the literals are represented in using one node in each layer. There is a big difference, but let's take an example to understand what I'm talking. So let's go back to our block world problem. So let's say this is my unit state. So unit state is A and B and C. And my goal state is A, B and C, right? A, B and C. Okay, so this is my initial state and this is my goal state. In state space planning, how do you write this? You first have a node which represents the initial state. So let me draw it here. I can represent this initial state using a node. So let me quickly write it. So on table B, right? So B is on table, clear C, C is clear, on table C, C is on table, right? On AB, A is on B, A is on B, and clear A, right? So clear A is what? So clear A means you can pick it. Right? So this is the whole thing I am representing this particular configuration. Now I have some operation like put on table A. Let's say I have an operation called put on table A. This is an operation or action. So put on table A. What are the conditions of put on table A? It should be clear A. That's one of the preconditions. That's correct. The second precondition is it should not be on the table already, right? Yeah, empty-handed or we are not talking here because the initial state is not discussing that, right? Initial state is only this set of states, whatever is given in this slide. So another thing is A, like put on table A. If A is already on table, you are not going to put, right? So A should be on some top of something. So for example, A should be on top of B, then we can do that. So that's a precondition for put on table A. And once we do put on table A, it will give us some effect, and that I can represent as another graph, another node in the graph, the state space graph, right? So this is state space graph we are trying. So what will happen? This will lead to on table, uh, on table B, right? Clear C. It will also have on table A. It will also have on table C and clear A. And as you can see, this actually corresponds to this particular state, right? So these are the same thing. But this axon has given us one state. Similarly, if I have a different axon, right? Different axon, let's say my axon is stack A on C. I can always do that. I can pick the A and I can keep that A to C, right? I can pick A and keep that to C. So that will give us something like B and C and A. All right. So this will give us B, C is on A is on top of C. So this is stack AC operation. What are the precondition of a stack AC? Stack AC, anyone? So stack AC means C should be clear, right? So C should be clear, and A should also be clear, right? A should also be. So this will give me another state. I can also write this, all these things, and this will give us another state. And this I can keep on doing, and it can give me at every state I can apply action to get another states. This is what is called. This is what we do in state space planning. Now, in the graph planning, that's not the case. The graph planning, what we do is very different. So what we actually do here is start with the initial state. Okay, so let me start with the initial state. So graph planning, the graph is layered, right? Graph is layered. So for example, this is layer zero. Layer zero will be always be literals or prepositions, right? So this will be like on table, B, clear, C, then on table C, clear C, on table C, on AB, on A, A is on B, and clear A. This is my layer one, layer zero, sorry. Layer one will be set of all the possible actions, right? So in the whatever actions you can apply in this, they will come here. So here, one of the action I can do is like, let's say stack AC, and then maybe I can also do put on table A. Right? So I can do this type of, I can do several other operations. These operations are denoted using a rectangular box, and they are connected with edges, uh, which are called precondition edges. Using maybe I can use precondition edges to show in red. So this is the precondition for this. This is the precondition for this. Similarly, for this, the preconditions are on A, B, and this. Right? So far there is no difference. So far, if you see, there is no difference. Now the difference will come in the label 2, right? In label 2, what we do is we only have one node in the label 2. We have only one node, right? So all like literals will be combined in one node. So when I say combined, all the things which are going to produce using the effect of these guys called stack SE or put on table, they will be clubbed together and have something like all the things like on table, B, and on. AC on table E and clear C and on table A and clear A. So you can see I am writing all the possible things which are happening after applying these operations. Of course, the correction will be like we also have the corrections. You can draw it here. The effect correction of stake AC will be like connected to on AC because that's the effect of that. Put on table A will be connected on table A. That's a positive effect as of now. Then we have negative as well. We'll draw that. But this is the notion. So the notion is in the graph planning, what you are doing is you start with the initial state, right? All represented as one. In layer one, you have the state. Sorry, you have the operations. In layer two, you have all the literals after applying these operations. Layer 3 will be operation on top of these literals, and layer 4 will again be literals. So yes, so there will be issues like contradiction, right? So they will be marked using mutual exclusion, right? So there is something called mutual exclusion. So they think that those things, those operations, even some operations can be mutually exclusive. You cannot really apply two operations simultaneously, or some literals can be also mutually exclusive. They will be marked using mutual exclusion or mutex type edges. We'll see what all edges are going to be there in the next few minutes. Then there will be such muted things, and then what you see finally in this state, right? So this is, let's say, your sub-state. You see that either the goal is achieved or not. So if goal is achieved, you backtrack and see what can be done, what needs to be done to achieve that goal. So only that your number of nodes in the graph is not exploding, right? So that's what you are trying to do with this, as compared to a state space where the number of nodes in the graph can explode, can be exponentially high in case of lot of operations. But here, that is not happening because it's kind of an only thing is the size of these nodes will keep on growing. That's there, you see that. But otherwise, they are just one node. And in that one node, you see, okay, this is satisfied, this is satisfied, this is satisfied. And that's what you worry and you backtrack what needs to be done for satisfying that. Is that clear? What is the difference between these two things? Okay, so now we'll move to defining this planning graph, like we have already seen, but in a more formal way. There is no meaning associated with edges in plan. Yeah, so there is no meaning, but there is some meaning. Like each of these edges are of different type. You'll see there are four types of edges in graph planning algorithm, and one of them is like precondition, one of them is effect, then negative effect, and also mutex. So they have that way they have some meaning, but they are just collecting these notes. Okay, let's into very interesting concept. This idea of planning graph. So, what is a planning graph more formally? Planning graph is a layered graph, right? So it is a layered graph. Is a layered graph with two kinds of layer. Two kinds of layer. first one are the literals. They are in the sorry, literals proposition. Yeah, the same thing. These will be in the even layer. Literals will be in the even layer, and axons will be in the odd layer. The first layer is a literal layer which shows all the literals that are true in the initial layer, right? This is into definition is not ending here. Then we say that first layer is the literal layer, right? First layer is the literal layer. We shows all the literals that are true in the initial layer. Right? So this is like us to show the init layer or initial state. And then literals and consecutive literals are only through problems. Okay, so that's another thing which we'll talk. And then let us talk about edges. Right. So this is we discussed that these are the literals. What are the edges? So there are four kinds of edges. Okay, let's look into that. So maybe we can draw them first, and then we can see between them. So okay, so the literals is just literals, four literals, and then the box. This box is this is a semantic representation, okay? And then there are some other layer. What are these dots? These dots are literals, right? And this is level 0, level 1, 2. It can have more levels, right? It's not like it's ending in the level 2. So the first kind of edge is called precondition edge. So precondition edge will be from level in this example, from which level to which level, precondition edge. Precondition edge will be from which level to which level in this particular example, L0 to L1, correct? So it will be L0 to L1, and let's maybe use some other color to distinguish them. This is red color, so that red color is precondition. There can be more precondition to this. Right? This is precondition edge. Every action has a precondition, and that's it. Second is positive edge. Positive edge. What is positive edge? This is the positive effect of an action, right? So each action has some positive and negative effect, right? So for a positive effect, we show that using like line, and here I'm showing them like this, okay, like this, maybe like this. These are positive edges, okay? And then the third kind of edges are negative edges, right? The negative edges as an action of something, if the next thing is not true, right? So then you add a negative edge. For example, I'm using dotted lines. edge is negative edge. We can write it. These are red lines, these are black lines, and these are dotted lines. All right. So this is negative edge. Maybe some negative edge will come up. And the fourth edge, which is also very important, is a mutex edge. So mutex, or in fact, there is a fifth kind of edge also. We need to stop that as well, but we'll stop that. But let's maybe first let's stop the fourth, not mutex, but something else. So there is no op. No op is no operation edge, right? No operation edge is you just take all the literals as such and you copy that from L0 to L2 and from L2 to L4. You just copy. And you copy. So for example, if this literal is there, I'll just copy it here. This is there, I will just copy that there. There, this is already copied. This is there, this is already copied, and that's all. So I'm copying everything from L0 to L2 and from L2 to L4 and L4 to L8, L6 and so on. Copying the previous ones using no of edge. No of edge, I am showing it using, let's say, yellow line here, right? They are no edges. You can see the size of the number of literals in will going to increase monotonically in this setup, right? So the number of literals in L0 will be less than number of literals in L2, and it will be less than or equal to in the number of literals in L4 and so on. There is no op edges using yellow line, right? Yellow line, and the fifth kind of edge is called mutex edge. Right? So what is a mutex edge? So it links mutually exclusive propositions in the same layer or two actions in the same layer. So it is a connection between two nodes in the same layer, right? So mutex edge is that very different. Mutex edge is always a connection between the two nodes in the same layer. It only says that linking two mutually exclusive propositions. So maybe let's say read, let's say this guy and this guy is mutually exclusive. Then you say why mutually exclusive? Let's say something is saying that clear C, and something is saying that B is on top of C. These things are mutually exclusive, right? So they cannot happen together. So all those mutual exclusive things you link in the same layer. Even some actions can be mutually exclusive, so you link that using dispute exchanges. All right, so these are the fifth kind of edge. And this is in this example, I'm showing it using green color, green light. Okay. Of course, this light color may not be visible for you guys currently, but when I share this PDF, you can easily see and make sense of these things. Okay, so now what is this mutex thing? Okay, so this no op edge or is also called maintenance edge. Right? So you maintain that. That's another thing. Maintenance edge. Look into. Okay, that's fine. Uh, So let's say mutual exclusive, right? So let's understand that a bit more. Uh, Mutual exclusive. Mutual exclusive. Yeah, yeah. So there are kind of edges. That's not correct on that. This is not correct. This is five kind of edges are there. So mutual exclusive. Let's say maybe mutual exclusive. They can't be both be done on the same state. They cannot be done in the parallel, right? When two axons are mutex, we saw that in our graph by drawing an arc between them. So let's say these are the mutex things. Let's say this is A is an action, B is an action, C is an action, let's say, and let's say this is a mutex line, and this is another mutex line. If this is the case, that means if you do A, you cannot do C, right? But you can do B because A and B are not correct. If you do C, you cannot do B or A, right? So if you do C, you cannot do B and A. You can think of many examples of visual exclusive actions. So that's I'm leaving it to you. Uh, what are the mutual exclusive actions? Normally, it should have inconsistent effect, right? So when we say two actions, maybe take another slide here. Sorry, right. Uh, so we say two actions A1 and A2 are mutually exclusive if if they have an inconsistent effect. First is inconsistent effect. Second is interference. We'll see what all these things are. Interference. And third is competing needs. What is the inconsistent effect? Effect of one action is negation of another, right? If effect of one action is negation of other, if that is the case, they are mutually exclusive. Interference is one action deletes the precondition of the other, right? One action deletes the precondition of other. Oh, so only linear ordering of two actions would be feasible, right? So that's interference, kind of very similar. Competing needs is actions have preconditions that are mutex at label I minus 1, right? So if they are mutex, so competing needs means, let's say you have a precondition. So let's say this is a preposition layer, position layer, and this is your action layer, this action and this action, right? The actions have preconditions that are mutex at level I minus 1. So they are, let's say, so this is showing precondition, this black arrows, and if these are, let's say, mutually exclusive. So precondition is mutually exclusive. That's a then the action here will also be mutually exclusive, right? Because preconditions are mutually exclusive means you cannot really apply same actions in the next stage. So these three things are there for mutual exclusion of x's. What about mutual exclusion of propositions? So mutually exclusive proposition. So there are two conditions when these the propositions can be mutex at label I, right? So one is they are negation of one another. They very simple. This you can easily identify that they are negation. For example, clear A and not clear A. They are obviously negation of one another, right? So example could be very simple. Let's say clear A and not clear A. This obviously mutex. Second is inconsistent support. That is, all ways of achieving propositions at level I minus 1 are pairwise mutex. So all ways of achieving the propositions at label I minus 1 are pairwise mutex. So in the previous layer, if they are pairwise mutex, and the next layer will also be, and they will be mutex. So that is very simple. Okay. So having these discussions around mutex, now we are ready to understand what how the algorithm really works like, right? With, let's see, we can explain the algorithm. Let's give an example. Okay, so the graph plan algorithm. Graph plan algo. Plan algorithm is a propositional planner, right? Propositional planner. And what you do is make a plan of graph of depth k, right? So first step is plan graph of depth k. Okay. Then search for the solution. If you found, good, right? So if you succeed, then return. Succeed, then return. But if you fail, right? If you do not succeed, then else k equal to k plus 1. That means you increase the size of the you depth of the graph, right? So you increase the depth of the graph. Go to 1, repeating this. So, what is the graph depth in this particular example? This particular example, the depth of the graph is you say graph is length 2. So what you are going to do in graph planning is you first obviously you expand to first layer, right? And go to L2. And in search in layer 2, if goal state prepositions are there or not, right? If they are there, you backtrack and find the solution. But if they are not there, right? Yeah, depth of this graph is just one, not two. And if they are not there, you expand the graph by adding two more layers. Right? So again, that will be graph length and get. So that is counted based on number of Excel layers, not the number of proposition layers. Number of Excel layers. Okay. So we are going to see one example. Let me maybe we can take a 1 minute or 2 minute break here, and we can try to work out. Hello, am I audible? Okay. The problem is I'm trying to share something, but it's not coming up. Just a minute. Anyway, so at least we can do this. Just a minute. It is here. I'm just trying to show some example of this graph planning. Uh, okay, let's do it. So what we'll do is we still have to complete some part. So next week, Saturday, we can meet. We can summarize the things and also complete this particular part by taking one example to understand the graph planning. But roughly, the idea is more or less clear to you guys. Uh, in the next lecture, we can do it. Okay. Thank you. And anything else to be done today? No. Okay, thanks. So next week, Saturday, we can meet. Let me see like when we can do. Maybe in the afternoon we can do. And we will also have a quiz that week. Assignment is already there, so try doing this. There is one assignment on graph planning, one or two question. Okay, thanks. Thank you guys. Thanks.